Space-time curvature is not what you think it is. And the picture in your head right now, that heavy ball sinking into a rubber sheet, dragging smaller balls toward it, is not just incomplete. It is circular. It uses gravity to explain gravity. The marble rolls into the dip because of the downward pull. But the downward pull is the thing you are supposedly explaining. That is like using a dictionary to define the word dictionary. And yet this image has survived for over a century. Textbooks print it. Teachers draw it. Pop science channels animate it in 3D and call it a day. The rubber sheet has become the meme of general relativity. It is wrong. Not a little wrong. Structurally wrong. The sheet is two-dimensional. Spacetime has 4 dimensions, 3 of space, 1 of time. And the most important curvature, the one that actually causes what we feel as gravity, is not bending space at all. It is bending time. But that part gets skipped because it is harder to animate and almost impossible to draw on a whiteboard. There is a better picture. And once it clicks, the old one looks embarrassing. Start with emptiness. No star, no planet, nothing. Just a 3-dimensional grid, a lattice of perfectly straight lines extending in every direction, evenly spaced, calm. Think of it as scaffolding for the universe. This grid represents spacetime when nothing is there to disturb it. Flat geometry. Euclidean. Boring. In this space, objects travel in straight lines at constant speed. No curves, no spirals. A rock drifting through this void keeps drifting forever. Newton would be happy here. Now drop a star in the center. The grid does not dent downward. There is no down, that is a rubber sheet idea, and we killed that already. What happens is stranger. The spacing between the lines changes. Near the star, the lines squeeze together. They bunch up, crowd into each other. Farther away, they gradually relax back to normal spacing. The grid is not broken. It is not torn. It is compressed. And that compression is curvature. Here is what makes this weird. The curvature is intrinsic. There is no external surface the grid is bending into. It is not like wrapping paper curving around a box. It is the paper itself changing its own internal distances. 2 points that look the same distance apart on a diagram are not the same distance apart in the actual curved geometry. The ruler between them stretches. Measurement itself is distorted. An ant crawling on this grid, trying to walk the straightest possible path, would end up tracing a curve. Not because something is pushing the ant sideways. Because straight has a different meaning in curved space. Mathematicians gave this path a name, a geodesic. In flat geometry, a geodesic is a boring straight line. In curved geometry, a geodesic bends. And every object in the universe, every planet, every satellite, every photon, follows one. This is the approach that ScienceClic pioneered in their remarkable visualization of general relativity. No force pulling. No force pushing. Just objects following the shape of the space they move through. The 3-dimensional curvature near a massive body guides every trajectory, every orbit, every fall. And this is what Einstein figured out, sitting at his desk in 1915. Gravity is not a force. It is geometry. Mass tells spacetime how to curve. Curved spacetime tells objects how to move. 2 sentences that replaced 300 years of Newtonian mechanics. But here is where most explanations stop. And where the real story actually begins. The curvature of space, the compression of those grid lines, accounts for only a tiny fraction of the gravitational effect we experience on Earth. The overwhelming majority comes from the curvature of time. And barely anyone talks about this. Near a massive object, time runs slower. Not metaphorically. Literally. Atomic clocks at different altitudes tick at different rates. A clock on the ground floor of a building runs, measurably, detectably, slower than a clock on the roof. They drift apart by about 90 billionths of a second per day for every meter of height difference. GPS satellites orbiting at 20,000 kilometers must correct for this constantly, multiple times per second, or your position on the map would drift by kilometers within hours. When an object is sitting still in space, it is still moving. Through time. Every second, it advances 1 second into the future. That sounds like a tautology, but it is a real physical statement. Objects have a velocity through time, and in flat spacetime, that velocity is uniform. Everything ages at the same rate. Near a massive object, the curvature of time changes that rate. And this creates something disturbing. The side of an object closer to a mass experiences time more slowly than the side farther away. There is a gradient, a tilt. And without any force at all, the object naturally drifts toward the region where time passes more slowly. That drift, that gentle, inexorable sliding down the time gradient, is what we call gravity. Think about that for a second. An apple falls from a tree not because a force pulls it down. It falls because the ground is aging more slowly than the branch. The apple follows the geodesic that takes it toward slower time. Gravity is a side effect of uneven aging. The metric tensor is the mathematical object that encodes all of this, the shape of spacetime at every single point, in every direction. Think of it as a 4x4 grid of numbers that tells you, at this location, here is how distances work, here is how time flows, here is where geodesics curve. From the metric, you can calculate every orbit, every trajectory, every gravitational interaction in the entire universe. For the Sun, the curvature is gentle. Light grazing its edge is deflected by 1.75 arcseconds, about 1/2000th of a degree. This was measured during the total solar eclipse of May 29, 1919, when Arthur Eddington photographed stars near the eclipsed Sun and found them shifted from their expected positions by exactly the amount Einstein had predicted. That single photograph ended Newton's 3-century monopoly on gravity. In one afternoon. For a neutron star, the curvature gets violent. The mass of 1.5 suns, sometimes more, crushed into a sphere roughly 10 kilometers across. Light bends visibly. Geodesics spiral. Clocks near the surface run at 70% the rate of clocks far away. The grid is so compressed near the surface that a straight line drawn between 2 points on opposite sides takes a path 30% longer than you would expect from flat geometry. But even that is not the extreme. For a black hole, the curvature reaches a point where the mathematics itself breaks. The grid lines converge. They squeeze past infinite compression to a single point, the singularity, where density, curvature, and every number you can calculate all blow up to infinity. The geodesic of any object crossing the event horizon leads to this point. Not through space. Through time. The singularity is not a place you can avoid by steering. It is your future. As unavoidable as next Thursday. The rubber sheet showed you a dip. Reality shows you something far more unsettling. A universe where geometry replaces force, where time bends more than space, where the straightest possible line through the cosmos is a curve around a star, and where falling is not falling at all, it is following the path of slowest aging through a landscape of warped clocks. And gravity, the thing Isaac Newton called a force between masses, the thing that holds you in your chair right now, is just the curvature of time. The curvature that holds every planet in its orbit, every galaxy in its cluster, every photon on its billion-year path through the void. All of it, following geometry shaped by mass and motion. The same geometry that distorts the grid, that curves the lines, that bends time itself. This visualization reveals something Einstein himself struggled to see. Gravity is not bending space. It is bending time. And if time can be bent, it might also be reversed.